Hello everyone. Today we're going to shortly review the paper Deep Vision Transformer Features as Dense Visual Descriptors. This paper studies the use of features extracted from a pre-trained vision transformer as visual descriptors for several applications. These applications include co-segmentation, which segments the foreground. Then there is part co-segmentation, which semantically co-segments common object parts. And point correspondences, which can find matching key points between two images. Just a quick note, the vision transformer used in this research is Dino. Now, let's have a brief overview of Dino. Dino is short for self-distillation with no labels. It is a self-supervised network which uses a self-distillation teacher-student approach. The teacher and student network are both vision transformers with different parameters. Attention heads of Dino generate salient foregrounds that can be used for image retrieval and object segmentation. Recent research treats the pre-trained Dino network as a black box. This means that usually the features extracted from the last layer are considered. This paper examines the deep vision transformer features across layers and dives into the different facets inside each layer, which includes the keys, values, and queries of the attention layers.
Now let's take a look at some parts of the vision transformer architecture. The image is first divided into non-overlapping patches. These patches are then processed into spatial tokens through linear projection, yielding the corresponding queries, keys, and values, and each can be used as patch descriptors.
Next, let's examine the representation of features across layers. Here, we have a visualization of deep features via PCA applied on supervised and self-supervised vision transformers and CNN ResNet models. In a CNN, early layers detect basic features like edges, while deeper layers capture higher-level concepts. As illustrated, the CNN ResNet trades special resolution with semantic information in the deeper layers, leading to lower resolution and poorly localized semantic details. On the left, we have the Vision Transformer layer's feature visualization. Vision Transformer maintains special resolution throughout its layers and has a receptive field covering the entire image. The shallow features capture positional information, while deeper layers emphasize semantic features. What is really interesting is that the intermediate features contain both positional and semantic information.
Let's move on to a representation of different facets of vision transformers. Here, the similarity between a feature associated with the magenta point in the source image is computed for intermediate features and last layer features. On the right side, the resulting similarity maps are shown when using different facets of Dino as features. For each facet, closest point in the target image is marked with a unique color. It is clear that the keys provide a slightly better representation. For example, they depict less sensitivity to background clutter than the other facets. Now, let's take a look at the pipeline for co-segmentation and part co-segmentation. For co-segmentation, a clustering and voting approach is applied. As displayed, the input images are fed separately to Dino and the key descriptors are obtained. All the extracted descriptors are then clustered together by k-means clustering. The saliency maps are also obtained from the self-attention maps. Then a simple voting procedure is used to select clusters that are salient and common to most of the images. And as a result, each cluster is assigned as foreground or background. To further co-segment the foreground objects into common parts, the clustering step is repeated only on foreground descriptors. The descriptors of common semantic parts across images are then grouped together. Here we can see some examples which show the applications of the co-segmentation and part co-segmentation pipeline.
Next, let's look at the key steps of the pipeline for point correspondences. First, the descriptors are extracted from mid-layer features, holding a balance between position and semantic information. Then, the saliency maps are extracted to understand the importance of different image regions. To identify potential matches, the similarity between descriptors are then calculated. To detect reliable matches, the notion of best buddies pairs is used by finding mutual nearest neighbors among binned descriptors. Then, a pair is removed if at least one descriptor is associated with the background. K-means clustering is then applied to capture high-quality pairs. Finally, the pairs are ranked based on their mean saliency value, providing a measure of their visual significance. Here, we can see an overview of the applications of this research. Thank you for your attention.